Hi, this is going to be lecture 26, and in this lecture we're going to actually use energy conservation, specifically when we have a combination of kinetic and one or more potential energies. So we're going to be looking at two particular examples, gravitational potential energy and elastic potential energy. So this energy is stored in the fact that an object is high up. Being high up means it can roll down a hill or fall down, gaining speed, and so when it's high up we can think of it as, okay, there's energy stored in its position. Elastic potential energy is when there's energy stored in the stretch or compression of something that's, well, elastic. Like a spring, for example, can be stretched or maybe squished, and there's energy stored in that. As soon as I let go, the spring will bounce back. I can imagine a rubber band or maybe a bowstring. Okay, a bow. About to shoot an arrow. I can pull the arrow back. As the bow bends, there's energy stored in that. As soon as I let go, that energy is converted to kinetic energy of the arrow. That's going to be one example we're looking at. In the process of this, I'm going to make some remarks here and there on energy conservation, just little details, little points of note. But what I want to emphasize is that in this lecture, I will not talk about why any of this works. So I will not sort of justify energy conservation. I will not prove it from some underlying principle. The goal of this lecture is to get a feel for how it works, how to use it, and then subsequently we can figure out why it works the way it works. This is different from how I think most textbooks will structure it. They will sort of derive energy conservation from scratch using a concept called work. And we're going to come to that later. But I think it's more productive if you first get a feel for why are we talking about this thing at all, what's its use, how do I use it, get kind of a hands-on experience, and then we can worry about justifying it. Let's get started. As I said before, each type of energy has a particular expression. It's a mathematical expression, and sometimes it can be extremely complicated and not really easily derivable. Say for the molecular structure, what's the chemical potential energy? That is a complicated question. It's not easily answered. I can't just write down a single expression, although in principle there's a mathematical way to calculate it. For the types of energy we're going to be dealing with right now, there is in all cases a fairly simple mathematical expression. The energy of the kinetic energy of an object, that's the energy associated with the motion of the object, is given by 1/2 times mass times speed squared. Why? Never mind that. We'll come to that. We'll figure out why is the speed squared. What's up with that? Why the half, right? We'll get there. But right now we're just going to use it and show that it works. Gravitational potential energy of an object. So that's the energy associated with, as I said, being high up on a hill or high up in the air, and that allows you to potentially gain a lot of speed, right? So potential energy is potential because it can potentially turn into kinetic energy. That's given by the mass of the object times g, the strength of gravity, the 9.8 meters per second squared on Earth, or 3.7 on Mars, or 25 on Jupiter, wherever you're at, times the height of the object. Note this expression only works, it's kind of the small print here, if you're near a planetary surface. So if you're out in space and you want to figure out the gravitational potential energy of the solar system, well, this is not going to cut it, right? There's another expression we're going to come to when we study Newtonian gravity. And finally, another example we're going to be looking at will involve elastic potential energy. That is the energy stored in a spring or rubber band. That's given by 1/2 times the spring constant. And the spring constant is really a kind of a fancy word to mean the measure of toughness of your spring. This is this thin little wound wire, very flimsy. So how is the toughness? H in there. Or is it something sort of made with firm metal, like the like in a bike, right? Like the spring in a bike, you bounce around on your bike, you land, or in a car, right? Suspension. Those springs are extremely tough. They'd have a very high spring constant. It's sort of a measure of how much force does the spring pull back with, or does the rubber band pull back with, per distance that you stretch it. Called the spring constant, and then the potential energy is 1/2 times that, times the amount by which you stretch or squish your system, your spring for example, squared. Why? Let's not worry about it. Let's just learn how to use it. We're going to look at a series of examples. Here's example 1. Imagine a brick, and the brick falls from a height of 5 meters. What is its impact speed? Let's just drop from a height of 5 meters. So my height is 5 meters. We're asking, if I drop it from this height, how fast is it when it hits the ground? Now actually you can solve this problem based on the kinematics you know from earlier in the course, and the fact that you know the acceleration of the brick, assuming it's on Earth, is going to be 9.8 meters per second squared. But we're going to solve it using energy conservation. So here's how we're going to do this. We're going to ask, what's the energy up here at the start? Then we're going to ask, what's the energy down here just before impact? Of course, the final speed, after everything is said and done, is going to be 0, but because the thing is stuck in the ground. But it is after it has interacted with the ground. I care about what's the speed with which it hits the ground. So I really care kind of the instant just before it hits the body. So here's how we think about the situation. We're saying the total energy here is the same as the total energy there. So the total energy at the start is equal to the total energy at impact. Okay, what types of energy are there? What kind of interactions are important here? Well, why is the brick falling? Because of its weight, because of gravity. So I'll need to take into account gravitational potential energy. Is there motion? Yes, there is. So I need to take into account kinetic energy. Is there anything else? Are there maybe any electrostatic forces? No. So I don't have to worry about electric potential energy. Like I wouldn't know where to start there. It's okay, it's not a relevant interaction here. What about is the nuclear configuration changing? Are the nuclei of the atoms making up the brick changing? No. So I don't need to include any form of nuclear potential energy. Right? Most of those energies that we wrote down in the last lecture are irrelevant for this scenario. What matters is the gravitational potential energy and kinetic energy. So we're going to say the kinetic energy, I'm going to abbreviate this KE at the start, plus the gravitational potential energy, gravitational potential energy. I want to abbreviate potential energy, kinetic energy every time because we're going to be using it so much, right? At the start, those two, they each change as the thing falls, but their sum, the total, stays the same. That's the kinetic energy at impact, at the moment of impact, plus the gravitational potential energy at impact. Right. So now I can write down expressions for each one. Well, the kinetic energy is 1/2 mv squared. 1/2 mv squared. Now v changes because the thing is falling, so I'm going to make sure I'm going to take the velocity right at the start, plus mgh, and that's the height. M of the brick doesn't change, g doesn't change, we stay in the same planet, presumably Earth, and h is the height at the start, but that can change later, so I'm going to put a subscript to the quantity that's changing. Where did I get those expressions from? Well, they're exactly the ones we wrote down here without explanation. We're using this one and this one. 1/2 mv squared mgh. And then these ones together, well, they're going to be equal to the same sum, but considered at the time of impact. So that's 1/2 mv impact squared plus mg times the height where the impact happens. Of course, if I could consider any point in the middle too, say this point here where the brick is right now in this action shot, right in the middle, then I could say at this point, right, the total energy is still the same, and I could say if it's fallen 2 meters, how fast is it going there? I could also work that out. But right now we just care about the beginning and the end, so we don't worry how the energy is distributed in the middle. I will just compare the beginning and the end. I picked the 2 points which are relevant, about which I already know something. So what do I know about each one? Well, I know the mass. Actually don't know the mass, but that's okay. Why is it okay? Because it cancels out. Right, the mass appears in every single term here, so it can cancel it out. And that's just a special feature of gravitational potential energy that includes the mass. Then, what do I know? Well, I know the value of g for sure, and I know that the velocity at the beginning is 0. Because we're just dropping it. The brick doesn't start to fall with some initial push, right? We just drop it. It starts from rest, speeds up due to gravity. The height at the start, we know that's 5 meters. G, well, it's going to be 10. I know 9.8, but I don't care. It's 10. We have the luxury to live on a planet where we can make that rounding, route 9.8 to 10. We're on Mars, 3.7, bit awkward. But 9.8 is close enough to 10. And the impact speed, we don't know, but that is the thing we want. So I'm just writing down, we want this. G again is 10 meters per second squared. And the height of impact, what's that? Well, it's 0, because that's the ground, right? Actually, who says the ground is at 0 height? We'll talk about that in just a bit. So now I can solve it, right? Fairly straightforwardly. I have that 0, because a half times 0 squared is 0, plus 10 meters per second squared times 5 meters. That is equal to well, 1/2 times the unknown speed squared plus 10 times 0, that's just 0. Okay, that's easy enough. I find that the impact squared is going to be 2 times 10 meters per second squared times 5 meters. So the impact, can't see this, now you can, is the square root of 2 times 10 meters per second squared times 5. So what's this? 2 times 10 is 20, times 5 is 100, square root of 100 turns out to be exactly 10 meters per second. And that's the speed of impact. Notice that nowhere in this did I actually work out what is the total amount of energy. In fact, I could. And I could work it out at any point, and that value will then apply throughout. I can't actually work it out here because I'm not given a mass. You could imagine if I actually had a mass, actually given a value, say 5 kilograms, then I could actually get a value that denotes the total amount of energy that would be measured in joules, this sort of basic unit of energy. And we'll do the time of calculation down the line for sure. In the second example, we have a very similar situation with the same brick, and again it's going to go down by a height of 5 meters, but this time it's going down a hill, like the side of a hill. Now, of course, we could analyze the shape of the hill, work out with normal forces, what are normal forces, what's the acceleration down the hill, do kinematics, presuming we know enough about the shape of the hill to do that, and we could find the speed at the bottom that way. Now, it might be that we don't actually know the exact shape of the hill. Well, it turns out the shape of the hill isn't actually relevant for how fast you go at the bottom, at least if we assume that we can ignore friction, which we're going to do. It's a frictionless hill. Of course, there is no such thing, but let's pretend there is to keep our life simple. We'll think about hills with friction later on. So I'm going to identify the two relevant points that I can viably compare, namely the start up here, because I know how we start. We start at rest at a height of 5 meters. Any point in between I don't know enough about, right? And then the other point I'm going to choose to compare that with is the when you reach the bottom. I'll just label this by bottom. Why do I pick this point? It's my second point because that's where I want to find speed. That's what I'm being asked to find, as it were. Now, again, I'm saying the total energy up here is the same as the total energy down there. Right, so we start the same way. At start is equal to the total energy at the bottom. Okay, now what is the total energy? Again, what are the relevant energies? Gravitational plus potential. So gravitational potential plus kinetic, excuse me. Right, because it's gravity that makes us go down. Now you might say, hold on, when I'm on the side of the hill, there's a normal force, right? But a normal force is perpendicular to the direction of motion, so all it does is change direction. It will never make us speed up or slow down. Hopefully you remember that. If I get an acceleration or a force, right, that's perpendicular to the direction I'm going in, then that only causes the object to turn, not to speed up or slow down. Right? If you forgot about that, go back to the lecture on turning motion from a while back. The normal force is always perpendicular to the line of motion because it's sliding down a hill. The normal force is perpendicular to the hill, and therefore it's not going to add any energy. And again, we'll talk about that in more detail. We'll justify that more rigorously down the line. So I have gravitational potential energy and I have kinetic energy. So initially, I'm just going to write it down abbreviated now, and I'm going to stop color coding. I'm going to write kinetic energy subscript start plus GPE, gravitational energy at the start, is equal to kinetic energy at the end plus gravitational potential energy at the, I guess I called it the bottom, so it should at least in that sense be consistent. Bottom at the bottom. Okay. So I can now maybe ask the question, well, what do I know, what do I not know? At which quantities do I know? Well, initially, my kinetic energy, well, it's 1/2 mv squared, but it's just 0 because we start at 0. Plus, what's mg times height? What's the height? Well, the height is still 5 meters. It hasn't changed. Notice, it's the height, the literal vertical height, not the length of the ramp. Right? It's just the height. How high up is it? It's all that matters. And that is 1/2 mv, the speed now at the bottom, squared, plus mg h, and this is h at the bottom, and I think that is 0 because we're at the bottom. This is of course at the start. So now you notice, wait a minute, that calculation looks exactly like what we had there. Like if you compare it piece by piece, it's exactly the same expression. It's the same. Right? It's exactly the same. It doesn't matter whether the object is going straight down, falling, or whether it's sliding down a hill, assuming there's no friction. The speed at the bottom is going to be the same, right? This is the same, so everything is just the same as before. And I want to find that V bottom, everything said and done, is going to be 10 meters per second. Right? Because all the values that appear here are the same as before. H, G specifically. The M cancels out again. So it's interesting insight, right? That no matter what the shape of the hill, note we didn't know the shape of the hill, we didn't know the degrees, like how steep is it, it might even be on a curve like I've drawn it, doesn't matter. the speed at the bottom is exactly the same speed as if the object had just fallen straight down. And that's not necessarily something you would expect. If you think of it this way, if it's on a hill, then it has a lower acceleration than if it were just falling, because it's on a hill, it's sliding down a hill. You may remember g sine theta, that's the acceleration down a hill. But on the other hand, the hill is a longer path than going straight down. There's kind of more distance over which the brick can accelerate. Turns out those two kind of compensate in a sense, in a very concrete mathematical sense. You can show that if you take a ramp, work out the kinematics versus free fall. The effect is that the speed at the bottom is the same no matter how you get from here down to here. In practice, that's not necessarily true because there tends to be friction and that tends to act differently, whether you're in a hill or whether you're in free fall, maybe air drag, right? Real life is more messy, but in the simplified situation, the answer is going to be exactly the same. And you can think of any other shape of hill from here down to here, maybe a sort of steeper hill or just a straight ramp, doesn't matter. The speed at the bottom is going to be the same. It only depends on your initial height and what planet you're on. Right, and that's what we learned from energy conservation. Okay, let's go on to another example with gravitational potential energy. It's a little bit more complicated. So here we go. I have a car, and the car is rolling along, and it's rolling towards a hill, and it has to go up the hill. The hill is 2 meters high. It's going 6 meters per second down here. How fast is it going to be going when it gets to the top? There's no engine, there's no air resistance or friction either, but it has to go up this hill, and that is necessarily going to slow the car down. Let's figure out the speed at the top. So I'm going to compare the total energy here, the total energy here. This time I'm just going to label it on my diagram. Why not? Here my kinetic energy is mass times 1/2 times mass times v squared. I don't know the mass again. I don't need to know it to do a calculation, because in gravitational potential energy problems the mass will always cancel out. But just to do it a bit differently, I'm gonna say the car actually has a mass. So let's pretend the mass was given as 1,000 kilograms. Why not? Let's pretend it was given as part of the problem. We don't need it to to find the speed at the top, but let's assume this was given. So this allows us to actually work out a value for the kinetic energy. It's going to be 1/2 times 1,000 kilograms times 6 meters per second squared, and that comes to 3618 times 1,000, 18,000 kilogram meter squared per second squared. This unit, kilogram meter squared per second squared, it comes from kilogram meter squared per second squared. This unit I call a joule. So 1 joule is 1 kilogram meter squared per second squared. In this case, the total energy is 18,000. Total kinetic energy is 18,000 joules. What's the gravitational potential energy? Well, it is at the bottom, the hill, so I think it's fair to call it 0. 0 height, mg times 0, mgh. What about over here? Well, the kinetic energy is 1/2 times the mass times the speed at the top squared, right? V top, this was V bottom, let me abbreviate it V bot. And I don't know what it is. I know the mass, I was given a value, but I don't know what it is, so I can't actually evaluate it. The gravitational potential energy here, however, I can work out, and it's not 0. It's m times g times h when we add a top, and that comes to 1,000 kilograms times 10 meters per second squared times h, 2 meters. Notice the units, kilogram, meter times meter, meter squared per second squared, still the same. What does this come to? This comes to 1000 times 10, that's 10,000, times 2 is 20,000. Interesting. So one thing you notice is that in this particular example, it appears that there's less initial kinetic energy than there has to be final gravitational potential energy. So initial, and it's initial total energy, then gravitational potential energy needed at the top. Right? Because to be up there, the thing has to have 20,000 joules of gravitational potential energy. So how can that be? Well, this plus this is equal to this plus this. Right? Total energy is conserved. So that gives essentially two possibilities. The one possibility is that this value is negative. Minus 2,000, right? 18,000 is equal to 20,000 plus what? Oh, minus 2,000. Is this a possibility? Is the final kinetic energy negative? Well, no, that's nonsense. Why is it nonsense? Well, 1/2 times m times v squared. Mass is positive. You can't have a car that is minus 6 kilograms. In fact, our car is 1,000 kilograms. But it can't, no matter what it is, it can't be a negative number. And then v squared, well, it's positive because it's squared. Right? Positive or negative, whatever the velocity you squared, you're going to get a positive number. So the kinetic energy is always positive. So what does that mean? 20,000 joules, 18,000 joules. There's not enough energy to make it to the top of the hill. The car will run out of energy. Its kinetic energy is going to get turned to potential. It's losing kinetic energy as it goes up the hill, gaining gravitational potential, but it doesn't have enough to make it up the hill. So it ends up there and doesn't get any further. And then probably starts rolling back down. So it wasn't going fast enough initially. Okay, we're in trouble. So let's imagine you've done this, right? The conclusion is that you're not going to make it up. There's no solution to this equation. So maybe it was a little toy car, not a real car, and you pushed it, right? So maybe now, the second time around, we're going to push it a little bit harder. Let's try again. And now suppose we're going 8 meters per second squared. Initially, sorry, even meters per second, excuse me. Speed initially. Okay, so now we're in a situation where, let me just quickly sketch it again. 2 meters, here's our initial position, here's our final position. And here now we're going a bit faster. Now we're going 8 meters per second. This is still 2 meters high. Same hill. So now my kinetic energy would be 1/2 times m times v at the bottom squared. That's 1/2 times 1,000 times 8 squared. Woohoo! That's more. 64, half, 32 times 1,000, 32,000 joules. My gravitational potential energy is still 0 because, I'm on the ground, I'm in the bottom. Over here, my kinetic energy, the kinetic energy of the car rather, is 1/2 times m times the speed at the top squared, which I don't know, which I'm trying to find, right? This is what I'm trying to figure out. My gravitational potential energy at the top is going to be m times g times H. We actually worked this out already. That hasn't changed. That is still 20,000 joules. So now, this is 32,000, this is 20,000, so how much is this? Right, so the total here is 32,000 joules. The total here is 20,000 joules plus the unknown 1/2 times 1,000 kilogram times v squared. The speed at the top, of course. Okay, let's work this out. Those two are equal. That's energy conservation. The totals are equal. We can simplify this. 12,000 joules, 32 minus 20, is equal to 1/2 times 1,000 times v at the top squared. Alright, let's figure out what that is. I divide by 1,000, so these cancel these, 1/2, so I've got 24 is equals to v top squared. So the speed at the top is the square root of 24. And if you track the units, right, I stopped tracking units here, it's in kilograms. I divide joules by kilograms, I'm left with meters squared per second squared. And that of course makes sense. Then when I take the square root of meter squared per second, meters squared per second squared, I want to get this meter per second. Square root of 24, I'm going to be rough here, I'm not going to get my calculator out. It's about 4.9. So significantly slower than before, but definitely not 0. Slowed down, but it's still going. Now, we met a situation where there wasn't enough energy to make it up. Alright. Then, so we fixed it by going faster initially. Notice we solved this one numerically. We actually plugged in values. Turns out though, if we had not been given the mass, right, that was the initial problem setting, we kind of made this one up. Without the mass, you would still have been able to solve it because the mass would have cancelled out. In all those terms, when I set those equal, I could have cancelled out the masses just as before. So I kind of did a little bit more work than I strictly had to. One more remark. You might say, hold on. Who says that down here is 0 height? Right, that's what we said. This is 0 height. This is gravitational potential energy at the bottom. 0. Why? Who says that? Could we have picked, this is our 0 height. Maybe it's in some kind of ditch, right? And 0 height is here. This is like my flat ground, my reference height. Yes, we could have done that too. We could have picked this as our 0 height. What would have changed? Well, initially, we would have had minus m times g times 2, because we would have been 2 meters below 0, and then we wouldn't have had it here. So what does that imply? We would have had 12,000 here, and 0 plus 1/2 1 times the 1,000 v squared over here. So I invite you to actually work through that yourself. Solve the same problem, but let this be 0 height. If this is 0 height, then down here is minus 2 meters. So this is not 0. This is m times g times minus 2 meters. This, on the other hand, would be 0. What you'll see is that you're going to get exactly the same answer. In a way, you're kind of starting with this line here. It's algebraically equivalent. Right? It's just you kind of start with the, instead of having 20,000 joules here, this is not going to be there. And you have minus 20,000 joules over here from the gravitational potential energy. Just by changing where you define your origin. But it doesn't matter having plus 20,000 here or minus 20,000 here. That's algebraically the same. Right? You're going to get the same answer when you solve it. Work through this. Actually do it. Post the video right now. Solve the same problem again. 0 is here, this is height minus 2, make sure you come to the same answer. Here's our next example, example 4. You imagine you're drawing a bow. Right? Here's a bow. I've drawn it once the way the bow is just sitting there, and then you pull the arrow back on the cord, and it's going to bend the bow. And if you've ever actually looked at a bow being shot, you notice that the stretch is not in the string. The string doesn't really stretch. It's the bow that contains the flexibility, right? The bow itself. Either way, we can measure how tough it is, how tough the bow is, how hard is it to move it. And suppose for this particular bow, we find that it would take 300 newtons to pull it out to 1 meter. Now the bow doesn't actually go that far. You break it before you get there. But you could imagine that just means 30 newtons per 10 centimeter of draw length, for example. And the bow, it's not going to be perfectly constant, but it's a good approximation. We call this, it's called a spring constant, even though it's not a spring, it's a bow. Still referred to as the spring constant, or maybe we could call it more accurately the effective spring constant. Effective is kind of a word in physics that means it acts just like a spring constant. It's effectively, mathematically, like a spring. At least a good approximation. We then imagine that the arrow mass is 50 grams and we're drawing it to 60 centimeters from the start. The question is, what's the speed of the arrow after you let go, after it's leaving the bow? So let's look at the total energy. What are the relevant types of energies? So always you first want to identify the relevant interactions, so you know what types of energies to include, or if you can use energy in the first place. Well, it's not gravity that makes the arrow speed up, it's the elastic force. Of course, we could be more pedantic and say it's a normal force between the string and the arrow, but we can treat a bow as essentially a single object, and there's a tension in the bow. That would be another way to put it. Right, and with this energy, with an elastic energy, we can associate a potential energy. So we're going to use elastic potential energy. And if you look back to early in the lecture, I gave you the expression again. We didn't justify it, we're just working with it right now. It was it's 1/2 times the spring constant, the toughness of the spring. In our case, it's 300 newtons per meter, times by how much it is stretched or squished. Well, we can't squish a bow, but we can stretch it, and that distance squared. So what points are we comparing? We're comparing the point when the bow is drawn to when the arrow is shot, when it's leaving the bow. Right. For energy conservation to be useful, always compare two different points in time. So bow being drawn all the way. And over here, we're going to make like a little table maybe this time. The different ways of setting it up. We're going to make a little table. Over here, the second point, and we're going to put the arrow has left the bow. Hasn't traveled up or down. Of course, that would involve gravity. So this time we're going to set it up like this. I'm going to put, what's the kinetic energy, right? It involves motion of the arrow, so I have to take into account the kinetic energy. Well, when the bow is all the way drawn out here, you're holding it, nothing is moving. So that is just 0. But initially, the bow is drawn by 60 centimeters. So for my elastic potential energy, I'm going to write down 1/2 times K times the stretch. Maybe go technically the draw length in the case of a bow, squared, which comes to 1/2 times 300. The units is newtons per meter, but a newton per meter is also a kilogram meter per second squared per meter, or a kilogram per per second squared. Don't believe me? Don't believe that Newton per meter is the same as kilogram per second squared? Well, write newtons in terms of kilograms, meters, and seconds, and you'll see it from there. But then, of course, we're multiplying it by the draw length squared, which is 0.6 meters squared. Note that I'm converting this to meters because joules is defined in terms of meters. Okay, we can actually work this out numerically. This is going to be, so 0.6 is 0.6 squared is 0.36 times a half times 300. That's 150 times 0.36, which, if I'm not mistaken, comes to 54 joules. And that makes the total energy at the beginning, while the bow is all the way drawn. Of course, if you're an archer, you don't want to hold it like too long because it makes your hand shake, because it requires a constant force. So you just want to draw it and shoot, and that's part of the skill of being a good archer, is being really fast at aiming, fast and accurate, so your hand doesn't get tired while you're holding it. Beside the point. Total is 54 joules. 0 plus 54. Okay, so that's my total energy at the beginning, before I have let go of the arrow. Now letting go of the arrow, and gradually, right, it takes time to get from here to here. Over that fraction of a second, the energy is gradually being converted from elastic potential that goes down as the stretch length goes down, and kinetic energy is being created in a sense. So elastic potential is being converted into kinetic energy. How long does it take? I don't know. Energy does not tell me about that, but it does tell me how fast the arrow is going. Final kinetic energy is 1/2 mv squared. There's only one v here. At the end, the bow is no longer drawn at all, so that is 0. So this is 1/2 times, well, m is 50 grams, so 0.05 kilograms, times the speed squared. And now those totals, those are the ones that I set equal to each other. These ones here. I'm not setting this equal to this, or this equal to this, or this equal to this, or any crosswise version. It looks as if I'm setting this equal to this. Right, this down here equal to this up here. But it's only because those two are 0. It's a coincidence in a way. Right? But now we're here. So now we can solve this for v. I'm just going to squish this calculation down here. I'm going to find that v is going to be the square root, because it's squared, 2 times 54 divided by 0.05, which I think is the square root, I think it comes to 2160. Now what's the square root of 2160? I think that's something like 46.5 meters per second. Right. So again, I found this by setting the initial total energy equal to the final total energy, and then solve for whatever the unknown quantity is. When I say initial and final, I really just mean the 2 points in this motion about which either I know a lot, like the initial one, or the one about which I want to know something, namely the point when the arrow has left the bow. Okay, so this was a different type of potential energy, but the logic is just the same. Whether it's gravitational, elastic, or really any other kind of energy. I'm going to leave you with a little question, a little problem for you to solve that involves pretty much everything we've learned today. But before I go there, here are some remarks, so something to be noted. It's things you can't calculate using energy. One is how long something takes, and you saw that with the falling brick versus the sliding brick. Right, the brick was sliding down the hill, as opposed to the falling one. They had the same speed at the bottom, but we didn't know how long each one would take to get down there. For that, you would have to use what you know about kinematics. And in fact, the one sliding down the hill would take longer to get to the bottom. But when it gets there, it has the same speed. It just takes longer. It also doesn't tell us about which way something is going. So in a couple of calculations now, we've worked out some kind of final speed, like the impact speed of the brick, the speed with which the arrow was leaving the bow, or the speed that the car had when it reached the top of the hill, if it reached the top of the hill. But none of those answers actually told us which way the object was moving, right? And energy just doesn't. Why can't it tell us about that? Well, because it's 1/2 times mass times speed squared, and there's no reference to the velocity, no reference to the direction. And energy can't tell us about how long something takes, because the whole point of energy is that it doesn't change in time. So energy just doesn't know what time it is, in a sense, because it's always the same. Okay, now let me leave you with a little puzzle. Here's the final problem. And I'm not going to solve this, I'm going to leave this to you to solve, or maybe we can talk about it in class. I imagine you are here standing on top of a bridge, and you have a bungee cord attached to you. You're about to just let yourself drop. The bungee cord right now is 20 meters long, right? It's unstretched. So it won't start stretching until you've jumped down and you've fallen 20 meters. It's a slack. Now imagine this bungee cord, 20 meters long. Well, when it does start stretching, it has an effective spring constant of 120 newtons per meter. So for every meter that it stretches, it's beyond 20 meters of length, it's going to exert a force that is 120 newtons per meter. Right? So when it's 21 meters long, it's 120. When it's 22 meters long, it's 240, and so on. You're 60 kilograms. Let yourself drop. What on earth? What is the lowest point that you're going to reach below the bridge? Or in other words, how high should the bridge be above that raging river down here so you don't get wet? Of course, if you do get wet, it's because you chose the wrong length bungee cord because the river was there first. But you get the idea. How far below the bridge do you end up at the lowest point of your fall? So ask yourself, what types of energy are going to be relevant here? There's a bungee cord where something gets stretched, but why are you falling in the first place? Gravity. So you'll have two different types of potential energy. Doesn't change anything. Total energy is what is conserved. Ask yourself, what's the initial speed? The moment you drop. Fairly straightforward, right? What's the speed at the lowest point? It's a turning point, right? You're going down and you're coming back up. So how fast are you actually going when you're at the very bottom? If you're not quite sure, maybe go back to the early kinematics lectures where we talked about that kind of concept. But in the end, what you're going to do is you're going to set the total energy here equal to the total energy at the bottom. Not anywhere in the middle. You don't have to go like, what happens at the point when the cord starts stretching. You don't have to have some kind of intermediate step. You can just compare the point at the beginning to the point that corresponds to the very bottom. And then solve for the unknown, the distance below the bridge. Be careful, it's a bit subtle because the cord doesn't stretch from the instant you fall. It only starts stretching once you've fallen already 20 meters. Solving this might involve using some mathematical techniques such as solving a quadratic. Who knows? Anyway, have fun with it. But here's the question again. What's the lowest point of the fall, measured as a distance below the starting point? Let's see what you can come up with.